Good evening, everyone. My name is John. Today we are going to be exploring or studying this key exchange um, algorithm together, the Diffie-Hellman key exchange algorithm. Notice it's not the only one. We also have one based on the elliptical curves. So the first thing I would want you to take note of is that this was the genesis of asymmetric schemes. The symmetric issue of key exchange was uh, a very big issue. We didn't have a way of exchanging keys in these symmetric schemes. So Whitfield, Diffie, and Martin Hellman in 1976 came up with this very profound idea. And the idea is that we could have this kind of computation, and this computation is having uh, exponentiation where commutativity was possible. Commutativity it's an arithmetic principle, like where we have a plus b is equals b plus a times b is equals b times a. So, but this was to be possible in exponentiation, not just in basic arithmetic. But before we dive into this, it's very important that we understand what this notation is. So this represents a multiplicative group of integers modulo p. When I say modulo p, I mean like in this set. This set comprises. Note that p here is prime. Comprises of elements from 0 to p minus 1 and p minus 1 inclusive that are co-prime to p. The co-prime, two elements are co-prime when the GCD is equals 1. And let's actually write this on the board. So when we say, for example, we have this integer group, so p is actually prime, so we can have like 5. So the elements of this set would be 0, 1, 2, 3, 4. So p minus 1, 4. And the basic idea of the Diffie-Hellman key exchange is that we could do this computation that a to the power of x, y is congruent to a to the power of y, x. So you see we have like commutativity in the exponents. So, but not just this, it has to be in a mode p world. P here is a prime number. So let's hold on to this idea. So maybe we should write it. Let's leave it here. I wanted to write it up. So why do we have this? Why do we have this computation here? It's because we actually want to find a way to exchange a common secret between the parties involved, Alice and Bob, or as many individuals who would want to communicate with each other. We can also see from this section that the fundamental key agreement technique is implemented for many open and widely used cryptographic protocols such as Secure Shell, TLS, IPsec, yeah. So, but that's not what we want. I just want us to understand how it works. So let's go to the basic setup. The basic setup is that, we said p prime, but we need a very large prime number. And we also need an integer alpha. So this integer and this prime are called the domain parameters or the public parameters. So let's go up a little bit so I can show you something here. Here. Okay. It's the idea that there is a third party, like these domain parameters are not just chosen randomly. We have, there is there is possibly a trusted third party that properly chooses and publishes public parameters, which is true, which are needed for key exchange. So these parameters, alpha and the prime. So it's also important to note that alpha is actually picked from, it's a concept of generator which you come to know is picked from 2 through p minus 2, the prime number minus 2. So let's now move down to how the algorithm works. Now, the Diffie-Hellman key exchange works this way. We're assuming that the domain parameters are public, like Alice and Bob has access to alpha and p. So we are assuming that. So what Alice does is that Alice would pick an A. So let's have it on the blackboard. I don't know why I keep calling this a blackboard. So how it works is that we're assuming that, let's assume that alpha, these two domain parameters, are public. So we have Alice. So what Alice does is that Alice would want to pick a private key. So we say Alice is going to choose A. A is like a private key, so we can call it private. So note that we said that she has to pick A from 2, so this A is going to be from this set 2 to P minus 2. So this is her private key. So we can say private key, let's make it very specific, private key of Alice. So she does this. She also needs to pick like a public key too. But how the public key works is that Alice is going to do key pub. It's actually going to make a computation. She's going to take this alpha and raise it to the power of this A modulo P. So this is, we're going to say K pub. Let's call it A is congruent to this. So she picks, let's take note of this. So this is her public key. So this is actually what she sends this A, she sends it to Bob. So Bob is on this other end. Now what Bob does is, Bob doesn't make use of this first, but Bob also makes a similar computation too. Note we said that alpha and P are actually public, like they are the domain parameters. So Bob would also choose a B, a secret key, let's call it K private B. So it's going to be like an element of, from this set, P minus 2. Bob also computes his public key. So we're going to call this B, which is congruent to alpha to the power of B mod P. So Bob also does this. And Bob sends this to Alice. Now, we should note that the basic idea of the Diffie-Hellman is that Diffie-Hellman said, okay, this key has to be, if we have, let's say, alpha, we don't need to use alpha, we can say a to the power of x to the power of y is congruent to a to the power of y of x in a mode p world. So this basic idea that when I have this, like this, these two guys are basically the same, y commutativity, x times y, so we're actually having commutativity in exponentiation. So when I hope you can see me, let's take it down a little bit. So let's start with Alice. So Alice has received the B from Bob. So Alice actually wants to, we are assuming we're now trying to establish the joint shared secret. So what Alice does is that Alice is now going to compute KAB, like this unique thing that exists between the two of them. So Bob is going to compute KBA. So Bob actually has B, Alice actually has A. So this is actually, he received B, so this is actually K, the public key of Bob. Let's say public key of Bob. He's going to raise it to his private key, the private key of Alice. That's what's going to happen, which is equal to public key of Bob is B, then the private key of Alice is A mod P. But we should note something. When you take a look at the public key of Bob, it's actually alpha to the power of B, A mod P. So let's see if Bob also gets the same thing. So Bob would also do the same thing. Bob is going to do the public key of A, because that's what he received. He's going to do public key of A and raise it to, he's going to raise it to his private key, the private key of B, so which is actually congruent to, he receives A, raises it to B, mod B, and we know that A is actually alpha to the power of A, B, mod P. So they actually receive the same thing. This can also be alpha, B, mod P. So the same thing, they actually receive the same thing. So, we would now go back to the slides. Yeah. So this is actually the basic proof. We actually proved it on the blackboard. We did here. We did prove it on the blackboard down there. Yeah. So we also have like a very, very basic example here to further clear our doubts that Diffie-Hellman key exchange was a very solid, ingenious idea. So we have the domain parameters 29, which is a prime number, and alpha, yeah. So what Alice does here is that Alice, let me zoom in a little bit. So Alice actually selects her A. Now note that A doesn't have to be like this, A or B, they don't have to be prime numbers. You can see that 12 is not a prime number. So we can recall from here, the set is actually from 2 through P minus 2. So even A can be 27. A can be, 10. It falls into, they are all elements of that set. We are taking note of P. So not like A can't be 30, A can be 29. So what Alice does is that Alice picks an A, then to compute her public key, she raises 2 to the power of 5. Note where we got the 2 from. 2 is part of the domain parameters. Mode 29. Now she gets 3. Now what this means is like 3 is actually the remainder when you divide 2 to the power of 5, which is 32 by 29. So 29 is like a world where the most you can see is 29. So we call it like in a modulo 29 world. So we have 3 here. Now Bob also does the same. So he sends this public parameter to Bob. Bob does his own computation, picks his B, raises the alpha to the power of his B to get his public key. This is 2 to the power of 12. You get a remainder of 7 when you divide by 29. That's why we have this congruent sign here. So this is congruent or equivalent to. So he sends his 7 to Alice. Alice sends, these are the public parameters or public keys. So to actually prove that they have established a shared secret, what Alice does is Alice receives Bob 7, raises it to the power of her private key, and she obtains 16 when she divides by in a modulo 29 world. Now, Bob also receives Alice's public key raised to the power of his private key. He obtains 16 also in a modulo 29 world. So you can see that the shared secret, the joint secret, so to say, is 16. Alice received 16 and Bob received 16. So this is really profound, I would say. Although it's susceptible to a man-in-the-middle attack. But it's so beautiful how these cryptographers think about things and make things work for humanity. So this will be it for today's study. There are a lot of very interesting things to study in cryptography. I hope to see you in our next study time. For all lovers of cryptography, stay connected, hit the subscribe button, and share your suggestions on the comments section. Have a wonderful evening. I am your one and only crypto baby, a crypto child, John. Bye.